All right, so our last talk is by Zhigang Bao, who wanted to come but couldn't due to some bureaucracy. So thank you very much. I know it's very early for you, but thank you very much.
That's okay.
Yeah, thank you so much for making it so early. So
Thank
the
you.
way it works with the mic here is that I will have to pass a microphone if anybody asks a question. So just
Sure.
watch out for that. All right, thanks very much. Please go ahead with your talk.
Okay, so first of all, I would like to thank the organizers, especially Benoit and James for the invitation, and also apologize for not being able to attend in person due to some visa issue, actually. Today I will introduce some recent results on the smallest eigenvalue of the sample covariance matrix. So it will be mainly a random matrix talk. I think in the talk there'll be a little bit of free probability, but it's really on the very basic level. So hope this still fits the scope of the workshop. This is a joint work with my postdoc Zhigang and my PhD Xiaocong. So we know that for the extreme eigenvalue of the classical random matrix, like Wiegand matrix and also sample covariance matrix, there's a famous law called Tracy-Widom law to describe the fluctuation of these eigenvalues. If you impose sufficiently strong moment condition or the condition on the tail of the distribution of the matrix entries, and it has also been well understood that what will happen if this moment condition does not hold. Say if you change the tail of the matrix entry from the lighter one to heavier one, and then it is also well studied for the extreme eigenvalue of Wiegand matrix or the largest eigenvalue of the sample covariance matrix. However, the understanding on the smallest eigenvalue of the sample covariance matrix is actually much less. So many things still is to be explored. The major reason is unlike the Wiegand matrix, so we know that Wiegand matrix, the smallest eigenvalue and the largest eigenvalue, they're basically on an equal footing since the spectrum is kind of symmetric. However, for sample covariance matrix, the behavior of the largest eigenvalue and the smallest eigenvalue could be very different. It's because the smallest eigenvalue is always non-negative. So there is a hard wall, zero, which prevents the smallest eigenvalue from being very small. So even the tail of the matrix entry is very heavy. Very often the smallest eigenvalue could be much more robust than the largest one. So in this talk, I'm going to show that indeed on the fluctuation level, there is still some phase transition for the smallest eigenvalue when you change the tail of the matrix entry from the light one to the heavy one. However, the phase transition is very different from the largest eigenvalue of the covariance matrix. In the first few slides, I will revisit some very well-known results for sample covariance matrix to specify some notations and scalings. So first of all, we are going to study the so-called sample covariance matrix, but with the null population. And I always use S of some matrix to denote the covariance matrix of this data matrix Y. So this data matrix Y is a scaled data matrix of the original data matrix X. So here, these X entries, they are independent of N. So this is a given array of random variables. And the typical size of this Y entries there of order 1 with square root of n. And we are going to make the following basic assumption on the X entries. So we will assume Xij to be IID for simplicity, although many results in this talk do not really require so strong assumption. And our default assumption on the moment is the mean 0 and the variance 1, although some results also does not require this condition in this talk. And the dimension assumption is a conventional one in the high dimensional setting for covariance matrix. We assume the dimension of the population vector and the sample size, they are proportional. So we denote by Cn the ratio between m and n, and we assume this Cn has a limit, which is a positive number. And we further denote by lambda s the eigenvalue of the covariance matrix. and we denote by mu y the empirical eigenvalue of sy. So this mu y is really mu sy. Okay, so for simplicity, I just write it as mu y. And I also denote by my the steady transform or the Cauchy transform of the empirical spread distribution. So the most basic result on the spectrum of the covariance matrix is, of course, the Martin-Kopast law. And so we already assume the second moment, the variance one condition, but here I want to emphasize this condition again. So under this second moment condition, we know the empirical spread distribution will be weakly approximated by the Martin-Kopast law. So the absolutely continuous part is like that, with two endpoints, lambda plus minus and p. So from the definition, you can see that if Cn does not equal 1, this left edge of the Martin-Kopast law will be away from 1. So it is strictly positive. And we also have the convergence of the steady transform, to the Martin-Kopast law steady transform, which can be computed explicitly. And we also know that at these two endpoints, lambda plus minus mp, the absolutely continuous part has a square root decay. So it's like the semicircular. And the one thing I want to mention is actually this square root decay can also be described by the steady transform. This is very easy to understand from the inverse steady transform thing. Okay, so particularly if we focus on the left edge, suppose I'm considering the case when Cn go to say infinity, which does not equal 1. Now in this case, this left edge will be away from 1, and we call this edge as a soft edge. And then around this lambda minus, you will have a square decay, square behavior. And this imaginary part of a steady transform will be like that. If you are outside of the support, the imaginary part is eta over square root of e plus eta. If you are inside the support, then this square root of e plus eta. So this is very easy to compute. And this is true for arbitrary eta larger than 0 for such an explicit steady transform. And later we will also use this description for the square behavior. So this is the case when we do have the second moment. And then you can also ask, how about if we drop this condition? Say if we consider the case with the heavy tail. And now here comes the result of the case when you do not have the second moment. And let's first start from the covariance matrix of the original data matrix. So this X is not scaled by anything. And in the light tail case, when you do have a second moment, we know this X should be scaled by square root of n. So the whole matrix is scaled by n. But in the heavy tail case, when the entry tail is of order s to the minus alpha for some alpha between 0 and 1, up to some slowly varying factor. In this case, we need to find another scaling factor, which is this a square. And this a square basically has an order n to the 2 divided by alpha. So when alpha is smaller than 2, this scaling factor is larger than n. Okay, so you need to scale it by some factor larger than n. And under this scaling, in this paper of Belinsky, Dembo, and Gunet, they show that the empirical spectral distribution of this scaled sample covariance matrix also has a weak limit. And so here I stated the detailed definition of the absolutely continuous part of this limiting distribution, but I'm not going to show you the detail. And there's only one thing I want to point out is that this limiting density has one very different feature if you compare it with the Martin-Kopast law, in the sense that the density does not vanish in a neighborhood of 0. In any neighborhood of 0, the density will not vanish. So this result does not depend on the value of C. Even C is away from 1, in a neighborhood of 0, the density still does not vanish. So if you go back to the Martin-Kopast law, in this case, we know that if C is away from 1, like that, then the left edge is away from 0. So in a neighborhood of 0, the absolutely continuous part does not have any density, right? In a small neighborhood of 0. However, in this heavy tail case, no matter how large C is, the density will not vanish in a neighborhood of 0. So this result actually indicates you that the smallest eigenvalue of this x is actually much smaller than this order. So it's much smaller than n to the 2 over alpha. So this gives you an upper bound on the smallest eigenvalue, okay, of the sample covariance matrix in the heavy tail case. Well, so these two slides show us the information about the global behavior. So these are the global laws. And then we may further check the behavior of the extreme eigenvalue. Now, so here comes the famous Bayin law. So in work of Bayin and also an early work with Krishnai, and they show that under the force moment condition, and also has the mean zero variance 1 condition, and further with the force moment condition, then the lambda 1 will converge almost surely to the right end point of the Marchenko-Pass law. And they also show the convergence of the smallest eigenvalue. And they were able to prove that actually this force moment condition is sufficient and necessary for the largest eigenvalue, but it was not clear whether it is a necessary condition for the convergence of the smallest eigenvalue at that time. And indeed, it was until 2015 that Tikhomirov shows that this condition is not necessary for the convergence of the smallest eigenvalue. Actually, the original mean zero variance 1 condition is already sufficient for the convergence of the smallest eigenvalue, okay, to the left edge of the Marchenko-Pass law. So this condition is the same as the global law. All right, so this is the first order behavior. And then you may further ask, what is the behavior on the fluctuation level? So this is the second order of the extreme eigenvalue. The most recent result is from a paper of Ding and Yang. So in this paper, they show that if the entry distribution decays sufficiently fast, faster than s to the -4, then you will still have Tracy-Wiedemann distribution for both the smallest and the largest eigenvalues of the sample covariance matrix. Now, so this condition, of course, is slightly weaker than the existence of the force moment. So we can call this as a weak force moment condition, okay? And so at a first glance, it's a bit surprising is because this condition is even weaker than the condition of the almost convergence. So this is the first order behavior. But this is the second order behavior, but it requires an even weaker condition. But the reason why it is not so surprising is because in this story, we're considering the weak convergence. But in the Bayin law, we're considering the almost sure convergence, so which is a stronger convergence mode. Okay, so this is why there's actually no contradiction in these two conditions. Now, so there are some comments on this result. And in this paper, they can show that actually this condition is sufficient and also necessary for the Tracy-Wiedemann law of the largest eigenvalue, if you assume the matrix entry to be IID. Now, but it was also not clear that whether it is necessary for the smallest one, okay? And actually, this result is an extension of an earlier, very original work by Li and Yin, which is on the same type of result, which is the necessary and the sufficient condition for the Tracy-Wiedemann law of the extreme eigenvalue of the Wegener matrix. But for Wegener matrix, you don't need to distinguish the smallest and the largest because they are symmetric, right? But for the covariance matrix, it is a very different story. So they cannot show that whether this condition is necessary for the convergence of the smallest eigenvalue. And another remark I want to make is actually they can derive this result for more general model. So they can do the proof for this model with a general population sigma, okay? And not just for the null case. And the last remark is this result, of course, is not the first result on the Tracy-Wiedemann law for covariance matrix. So there is a long list of reference trying to prove the universality, edge universality of the covariance matrix, but I'm not going to introduce them in detail. Okay. So this is the behavior of the extreme eigenvalue in the light tail case. And then you may wonder that what will happen if we drop this condition? Now, if we drop this condition, say if we consider the case when you do not have force moment, and so this is a result first by Soshnikov in the case when alpha is smaller than 2, and then further extended by Ofinger, Ben Hoos, and Pichet to the full regime of alpha larger than 0 smaller than 4. Now, if the matrix entry X have the tail s to the minus alpha up to some slowly varying factor, and then you will have a different law for the largest eigenvalue. It's no longer Tracy-Widom law. And also we know that in the latter case, when you do have the force moment, or you do have the weak force moment, and or you have the force moment, this lambda 1 is of order n. Okay, so this lambda 1 of Sx without any normalization, it is of order n. But in this heavy tail case, the order of this guy is also larger. And now the order is actually the so-called Bn square. So Bn is of order n2 divided by alpha. So Bn square is n to the 4 divided by alpha up to some slowly varying factor. So when alpha is more than 4, this guy again is much larger than n. And so under this scaling, the law is given by the classical extreme value distribution, Fresher law. So the reason why this classical Fresher law shows up is indeed because in this case, the largest eigenvalue is indeed given by the extreme value of ID random variable. So essentially, this lambda 1 is given by the maximum of all the entries square. Okay, so this is basically the largest entry square. And if you consider the first few largest eigenvalues, then this forms inhomogeneous Poisson process. Okay? And another remark I want to make is in a very recent work of Diacono, she can show that she can also show the distribution in the critical case when the tail is exactly of order s to the minus 4. Okay, so this was derived for the Wigner matrix, but it is quite convincing that you can also extend it to the largest eigenvalue of the sample covariance matrix. All right, so this is the story about the largest eigenvalue on second order. And now, before we show you the result for the smallest eigenvalue of the covariance matrix, I want to provide some very heuristic argument on why the behavior of the smallest eigenvalue could be different from the largest eigenvalue of the covariance matrix, at least on the first order. Because from the Bayin law and the Tikhomyov's law, we already know that the first order behavior of the smallest eigenvalue and the largest eigenvalue could be very different. So one requires the fourth moment and the other only requires second moment. So in this sense, the convergence of the smallest eigenvalue is much more robust. Now, so for simplicity, let me focus on the case when Cn is smaller than equal to 1. Okay, so m is smaller than equal to n. Now, we tend to consider the smallest and the largest singular value of the data matrix Y. So they are simply the square root of the eigenvalue of our sample covariance matrix. Let's record the variational definition of the largest and the smallest singular value. Now, so when we try to compute the largest singular value of the data matrix, we're trying to find some maximizer which try to make this the L2 norm of this vector as large as possible. Okay, so we know the typical size of this matrix entry, the Y's entry is 1 over square root of n. But if you are in some heavy-tailed case, there may be a few entries which are very large, okay, which are very atypical. They are much larger than 1 over square root of n. So now those entries we care is the entries which could be much larger than 1. So either it diverge along with n, or maybe it's much larger than some constant c, say some sufficiently large constant c. Now let's try to single out this kind of entry. So suppose this Y star has such an entry, okay, which is much larger than some constant, say. Now, if we do have such an entry, then at least we can choose some vector in this way that here this blue star is very big. So you can even just assume this blue star is 1, okay, and all the other entries are 0. Now, in this case, if you consider the product Y star and V, then at least the resulting vector will have one big entry, which is the red star times the blue star, okay, so which is just the size of the red star. So you can imagine that if there's one big entry in this Y, then the largest singular value will be immediately very big. Okay, so now you may think that when do we typically expect at least one big entry, so which is much larger than 1, say? Well, this is a very basic calculation. So you totally have n times m entry, right? And the expected number of some expected number of the entry, which is much larger than 1, say some constant c, is n times m times the probability of this y entry, which is the xij divided by square root of n, say larger than constant c. Now this guy, by our tail assumption, which is just of order n square, n times n to the minus alpha divided by 2. Okay, so this is just n to the 2 minus alpha divided by 2. Now, in case alpha is smaller than 4, then this number is much larger than 1. Okay, so you expect at least one big entry in this data matrix. So this is the reason why when alpha is smaller than 4, immediately the largest eigenvalue will be very large. So it will be very different from the light tail case. Now, for the smallest singular value, the story is very different because for the smallest eigenvalue, you're trying to find the minimizer. Okay, you're trying to find a v so that this L2 norm is as small as possible. Now, suppose this time we still have some big entry. So maybe not just order 1 number of big entry. So suppose there are a lot of big entry. Well, up to some permutation, we can move them to the left upper corner, see? Now, in this case, if all the big entries are here, then you can try to choose a V in such a way that only those entries, these blue stars, are large and all the others are small. So in this case, you're trying to avoid the big entry of the matrix. Okay. Now that means you're trying to choose a V living in the kernel space of the matrix of the big entry of the matrix of this Y. Okay. So now that means as long as the rank of the matrix of this red star is sort of low, so it is lower than n, you are always able to choose such a vector to avoid this big entry. Okay, so that means if the rank of the red part is a little on, then you can believe that the big entry of the y will not affect the smallest singular value too much. Okay, because you can still choose such a vector which is in the kernel space of those big entry. Now, so when you can ask, when will this happen? When the big entry, total number of the big entry, or the rank of the major big entry is of little o of n. This will be exactly the case when alpha is much larger than 2. Okay, so if alpha is much larger than 2, then this number is little o of n. So in this case, you can imagine that the smallest singular value will not be affected too much. So this heuristic argument tells you that why when you have second moment, the smallest eigenvalue will still converge. Okay, so it is very different from the largest eigenvalue. But of course, this argument is not fine enough for the second order behavior because this entry they may still affect the fluctuation a bit to a certain extent. Okay. All right, so now let's move to the second order. So what will happen on the second order? Now, in order, before I state my results, I'm going to make some additional assumption. Okay, so in addition to our basic assumption, like a mean zero variance 1, and for some technical reason, we need more assumption. So first of all, I assume the xij to be symmetrically distributed, and we also assume there is a non-zero density at 0. Okay, and further, I want to make a more precise tail assumption. So basically, we assume the tail is more or less exactly like s to the minus alpha. So here we do not multiply by some general slowly varying factor for some technical reason. Okay, and then we further consider the case when alpha is larger than 2. So that means you will have second moment. And we're not going to consider the case when alpha is smaller than 2. Because when alpha is smaller than 2, we have already shown you the global law. Even the global law is very different from the Marchenko-Pastel law. Okay, so even the scaling of the spectrum is very different from the light tail case. So this will be completely different story. So we will focus on this case, and sometimes we call it a semi-heavy tail case. Okay, and then for simplicity, we will also consider the case when Cn is smaller than 1. But when Cn is larger than 1, you can simply switch the role of n and m. So they are actually the same. But the regime we're not going to consider is Cn equal 1. Okay. Now, when Cn equal 1, this is a very different story. So this will be the hard edge story. Okay, so this is no longer the soft edge. So this will require very different arguments. So now we are going to consider the soft edge and also this semi-heavy tailed setting. Okay, and now here comes our findings. So we show that in this semi-heavy tail case, there will exist a random variable x alpha, depending on alpha, and the following statements are true. Now, first of all, for the smallest eigenvalue, we know the first order limit is still the left edge of the Marchenko-Pass law by Tikhomirov's law, right? But there is a random variable of smaller order. You need to further subtract by the smaller random variable, and then this difference will go to Tracy-Wiedemann law. And now this guy itself is random. And the difference between lambda m and this deterministic shift and also this random variable is of order n to the minus 2/3. However, the fluctuation of this guy itself may be larger than n to the minus 2/3. So actually, this guy has a fluctuation of order n to the minus alpha divided by 4. So you can simply compare the order of this two random variables. So this is of order n to the minus 2/3. And now this centered x alpha, this guy is of order n to the minus alpha divided by 4. Now, these two random variables, if you compare these two exponents, you can easily discover a phase transition. So when alpha is larger than a/3, say, when alpha is larger than a/3, this guy is smaller than n to the minus 2/3. Okay, so the randomness of this x alpha just doesn't matter for the limiting law of lambda m. So in this case, you still have Tracy-Wiedemann law for this lambda m. However, when alpha is smaller than a/3, then the fluctuation of this guy will dominate the fluctuation of lambda m. So actually, essentially, the fluctuation of lambda m will be given by the fluctuation of x alpha when alpha is smaller than h/3. So there's a phase transition happens when alpha crosses h/3. This is very different from the threshold of the largest eigenvalue, where the phase transition happens when alpha cross 4. Okay. So now actually the distribution of this x alpha is asymptotic Gaussian, and we are also able to compute the variance, limiting variance of x alpha. Now, another thing we need to mention is actually the expectation of this x alpha is also not negligible. So this guy is of order n to the 1 minus alpha divided by 2. So this shift in many cases is a very large shift if you compare to this fluctuation scale. So when alpha approach 4, this guy will approach to n to the power minus 1. So this is negligible. But when alpha approach 2, this shift will approach to order 1. So this indicates you strongly that when alpha go below 2, something very different will happen. Okay, this is indeed what you see from the global. Okay, so this shift is almost order 1 when alpha go to 2. So now, by now we are only able to show that the remainder order of this x alpha is a little o of n to the 1 minus alpha divided by 2. But an ideal case is you can further do the expansion up to some order which is smaller than the fluctuation order. So this would be the ideal case. Okay. Now you keep expanding the expectation of that until you get some area which is smaller than either of these two fluctuation order. But this is what we cannot do now by some technical reason. So we are only able to find the leading term of the shift. Okay. So now this is the case when alpha is generally from 2 to 4, but in the critical regime, when alpha is exactly a/3, and when you replace x alpha by ex alpha, we can also show that the limiting law is given by the classical convolution of the Tracy-Wiedemann and Gaussian. So these two parts, they are indeed independent. Okay, this is also what we can prove. So these statements, they give you a sort of complete picture, except for the remainder term of ex alpha on what happens about the smallest eigenvalue of the covariance matrix in the semi-heavy tail case. So there's a phase transition when alpha goes across a/3. So this is the main result of the talk. And so in the rest of the talk, I would like to show you a bit on the methodology level. So on how we try to prove this result. So very roughly speaking, we actually rely on the so-called dynamic approach, which has been developed by mainly by the Edish Yale School in the last decade. But to better illustrate the mechanism, let me start from the deformed Wigner matrix. Okay. So actually, what we are going to discuss, what we are going to use is the sample covariance concept part. But let me first start from the Wigner case. So suppose we consider such a Gaussian divisible matrix, and we have an initial matrix V, so which is a diagonal matrix, and you can assume this V to be deterministic. And very often in application, this is actually a random matrix, or the diagonalization of some random matrix, say the diagonalization of a general Wigner matrix. But in either case, we always assume this V to be independent of this GOE part. Okay, so the idea is to condition on this V. So you always regard this V as fixed, no matter it's random or not. And then you're going to use the randomness of this GOE. And so this guy in distribution, you can just regard it as a matrix value Brownian motion starting from V. And so this is a distribution at time t. Okay. Now, so the question is, what is the behavior of the, say, extreme eigenvalue of this HT? So you want to know that when this extreme eigenvalue, say, is like the smallest eigenvalue, have the Tracy-Wiedemann law. But you can imagine that if T is very large, this matrix will behave similar and more similar to GOE. So you can expect the Tracy-Wiedemann law when T is sufficiently large. But the dynamic approach tells you that actually you do not need to send T to infinity. Actually, you only need a very tiny GOE component to get the Tracy-Wiedemann law. So this is a so-called local equilibrium. Okay. Now, but the size of the T required to get the local equilibrium actually depend on the spectrum of this V. So basically, we require this distribution of the spectrum V cannot be too wide. Okay, so we need some initial regularity assumption on the spectrum of the V. So now to quantify the regularity, we're going to introduce a concept called eta star regularity, which is essentially given by the C transform of the spectrum of this V. So here again, we see the imaginary part of the C transform, which we have shown when we discussed the Marchenko-Pastor law. We say that when you want to describe the square root behavior, you can use the imaginary part of C transform. Okay, so here again, we have this square root type of result for the C transform. And here we basically choose 0 as the left edge of the spectrum of this V. Well, without loss of generality, we can always do that by shifting this V, say, okay? So we suppose this 0 is the left edge of this V. So that means the majority of the smallest eigenvalues are around 0. And now this result, this assumption is required only for eta larger than some parameter called eta star. So we do not require to hold for arbitrary eta larger than 0. Okay. So here the eta star regularity basically means that if you consider the eigenvalue, the smallest eigenvalues, say this is a cluster of the smallest eigenvalue. And now if you have an interval, if you find an interval I, so whose length is of order eta much larger than equal to eta star. Now you consider the number of eigenvalue in this interval and further divided by the total number. Now, if this guy is more or less given by the left edge of the Marchenko-Pastor law or the semicircle law, say this is -2 plus the length of I and the rho SC dx, say. Now, if this is the case, if I is that large, then we say this is eta star regularity or square root density on scale eta star. So basically that means if you choose an interval which is no smaller than eta star, then the behavior, the distribution of the eigenvalue will be more or less the same as the edge of the spectrum of the Wigner matrix or the sample covariance matrix. Okay, but if we consider some finer scale, say when the interval of I is much smaller than eta star, this may no longer be true. Okay, so we only need the square root behavior when eta is larger than eta star. Now, but this control in terms of the imaginary part of Stiglitz transform cannot tell you the behavior of a single eigenvalue. So this is just like the spike model. If you have one single eigenvalue, which is very far away from the majority of eigenvalue, this will not affect the estimate of the C transform. So we also require a lower bound of the smallest eigenvalue of Vi. actually we also require this smallest eigenvalue to be not too far away from 0. Okay, so this guy will also impose a lower bound on it, and also on scale eta star. And then the last condition is actually a very mild condition. We assume this operation norm of this initial V is bounded by some power of n. So in application, you can always do that by, you can always have that by doing some truncation of the original matrix, say. So this is actually a very mild condition. So very roughly speaking, the eta star regularity means the regularized density of the spectrum V has a square behavior, but on scale eta star, okay? Now, so suppose you have eta star regularity, then in this very basic fundamental result of Landon and Yao on the edge universality of the Dyson-Brownian motion, they show that as long as you run the Brownian motion after time t much larger than square root of eta star, then you will reach the local equilibrium. So the smallest eigenvalue of this deformed Wiegand matrix, a deformed GOE, will follow the Tracy-Widom distribution. Okay, and then of course the Tracy-Widom distribution for the smallest eigenvalue is around the left edge of the kind of the deterministic measure. Now that this deterministic measure is of course the spread distribution of the V and the GOE, right? So this is a convolution, free additive convolution of the distribution of V and the GOE. But for GOE part, we can just use semicircle to approximate it for simplicity, okay? So here, this edge, this shift can be identified as the left edge of the free convolution, okay? So this is just the free convolution of the V spread distribution with a semicircle. And now here we also have the scaling factor, as because you need to further adjust the curvature of the square root behavior to align with the curvature of the standard semicircular. Okay. Now, one thing we need to emphasize is when you use this result for a random initial condition, say, suppose your V initially it is a random matrix, not deterministic matrix. Even you already have this Tracy-Widom law, this may not be the end of the story because your shift and the scaling factors, they're both random because they are V dependent. Okay, so themselves are still random. So if you really want to identify the randomness of this lambda ht, you need to further discuss the randomness of this E minus and the gamma minus. Now, in many cases, when this V, say, is a diagonalization of the light tail Wiegand matrix, this E is actually almost deterministic. So you can estimate this E with a negligible error. However, if you are in the heavy tail case, this may be very different, okay? So this is one thing we need to notice. And now what we are going to use is actually the dynamic approach for the covariance analog. And we need the rectangle version of the story. So this is an extension done by Ding and Yang. So they prove that actually if you run a dynamic for this covariance matrix DD star, so DD star is our initial condition, and you add a Gaussian component, square root T of a W. So this W has IID Gaussian entries. And then after sufficiently long time T, you can also reach the edge universality, okay? Now the proof is not so much different from the Wiegand case because you can consider the linearization of this matrix. So the linearization is basically, again, a Wiegand type of matrix, although it has a block structure, okay? And so the mechanism is exactly the same if you can first show a regularity result of the spectrum of SD, say that there is a square root behavior on scale at a star, and then you run a Brownian motion and longer than square root of eta star, then you will have a Tracy-Widom law. But again, the problem is the edge and the scaling factor in this Tracy-Widom law, they're both D dependent, so they will be random again, okay? And you need to consider the randomness of this D matrix. And now, so how to apply this dynamical approach to our model? We actually rely more specifically on a work of Aguo, Lopato, and Yao. So this work was originally done for the bulk regime of the so-called Levy matrix. So that means Levy matrix means that you are in the regime of alpha smaller than 2, okay? So in that work, they introduced a decomposition for the data matrix. So the decomposition is slightly different from the decomposition I'm going to show here, is because we're in different regime of alpha, but the rough idea is the same. Okay. So what is the decomposition for our data matrix? Now, in many discussion of the heavy tail random variable, of course, we usually do a truncation of the entry with a large truncation level, and we try to get rid of the large part of the random variable for many discussion. And here we're also trying to cut off this large part as well. So the large part is those entries I call C entry. These entries, they are those larger than n to the minus epsilon b. So epsilon b could be a very tiny parameter. So that means basically these entries are those entries larger than of order 1, say more or less. Okay. And now, so this is a large entry, but we know the typical entry of the Y matrix is of order n to the minus 1/2, n to the minus 1/2. Okay. And but the difference from the classical truncation, we are also going to separate the small part of the entry. So the small part means those entry much smaller than the typical order n to the minus 1/2. So they are smaller than n to the minus 1/2 and further subtracted by some epsilon a. Okay, so this is a small part of the entries. So we have the small part, large part, and the typical part, we call it medium part. And now you further introduce two indicate function, Poisson and the chi variable. They are the Bernoulli random variable, which indicate the event whether this y is taking a large value or the typical value or the median value. Okay. And now if you have these 5 random variables, and now if you draw this random variable independently, all of them are drawn independently, and then you combine this variable in this way, you have these 3 random variables, the capital Aij, Bij, and Cij, and then you further form a matrix, and then you sum them up, then the distribution will be the same as our original data matrix. Okay, so you can call it a decomposition, or you can also call it a resampling of the data matrix. Now, the key thing is all these random variable, pi, psi, A, B, C, they are independent. But this matrix entries, A entry, B entry, and C entry, they are not independent. They are coupled via these Bernoulli variables. Okay, so although the dependence is explicit through this psi and chi, they are still not independent. Okay, so for many discussions, this will cause many troubles. And now, so sometimes we also combine this B and C together. You can call it a major part, and we write it as D. Okay, and now the key idea is the separation of this A part, this small part. So you may wonder that why do we have a separation for this small part in this discussion? It's because we want to replace this small part by a Gaussian component in order to get a Gaussian divisible model. Now, so this is a small part. Now, if we replace it by some square root t times w, which is a Gaussian matrix, and now the choice of this t depends on the variance of this A. So the variance of this A entry is of order n to the minus 1 further subtracted by 2 epsilon alpha, because this A entry is atypically small, right? So they're typically smaller than the typical size n to the minus 1/2. So this, if you choose this t to be like that, and this Gaussian entry, they are variance 1 over n, then these two guys, they will match up to actually 3rd order, not just the 2nd order, because we assumed our distribution of the entries are symmetric, right? So these two matrices, they match up to 3rd order, okay? Now, so you can even simply consider this Gaussian divisible model as a special case of our semi-heavy tail matrix, because this is still a semi-heavy tail matrix, although it has a Gaussian part, right? Because if you consider the tail, it will still follow the heavy tail with alpha from 2 to 4. So you can imagine that if the results hold for this guy, and if you believe the universality, then the result should also hold for the general case. Okay. So now the idea is we should first prove a result for this Gaussian divisible model, and via the dynamic approach, as we showed before, right? And then you do a comparison between this Gaussian divisible model and the original model via something called the green function comparison technique. Okay, so this is the basic proof roots. Now, let's first discuss a bit more about the dynamic approach. So in this part, we will indeed have an independent Gaussian added to this initial matrix D. So remember, this initial matrix D is B plus C, which is the typical part plus the large part, okay? And now, as we said, in order to use the dynamic approach to get something like a Tracy-Widom law, you will need a regularity of this D as an input. So you assume you need to have a result that the spectrum of the D, they're not that wide at the left edge, okay? So they have some square behavior on scale eta star. So this is what you need to prove. So now how to prove the eta star regularity of this D at the left edge? Now, if you think about the right edge, or if you think about the largest eigenvalues of this D, they will not be square behavior. They will not have square behavior because you know the largest eigenvalues of this heavy tail matrix, they will form a Poisson process. And actually, there's no square behavior, okay? But we already mentioned heuristically that the left edge have very different behavior if you have the second moment. And we tried to argue that as long as the matrix of the big entry is a low rank of n, then it's not going to affect the smallest eigenvalue too much on the first order. So now if we want to prove a regularity condition for this D, we can actually still use this heuristic. We're trying to get rid of this big entry, since we're going to get rid of the C entries. And then we're going to argue that getting rid of the C entry will not affect the left edge of this D too much. And then we can tend to study the left edge of this B. Then this B is a very nice matrix, okay? You can study the left edge by some well-established technique. Now, so how to get rid of the C entry? Now we're going to define two index sets. And so we record this psi entry as the indicate function of the Y entry to be large. So we collected them together as this psi matrix, okay? Now we're going to define a row index set, which is the set of indices, or set of the rows in which you can find at least one big entry. So as long as you find at least one big entry in this row, you just take it out and put it in this DR. Okay, so this is a row index set. And similarly, you can define this column index set. So as long as there's one entry in this column, you take it out and put it in DC. So now actually, when your alpha is larger than 2, this the size of this d alpha and dc, they are both smaller than n to 1 minus some epsilon, okay? Because this is basically just a basic calculation. This is also what we discussed in the heuristic arguments. And now I'm going to consider the minor of my original data matrix after I remove this rows in this dr and all the column. So I call them as a row minor and the d column minor, okay? And now by a very basic Cauchy interlacing, you can actually prove that the smallest eigenvalue of the sample covariance matrix of the original D is larger than the smallest eigenvalue of the sample covariance matrix of the column minor. But meanwhile, it will be bounded above by the smallest eigenvalue of the sample covariance matrix of the row minor. Now the row minor has a lower dimension, which is m minus the size of dr times n, the data matrix, okay? So this is a very basic Cauchy interlacing. Now, notice that for the largest eigenvalue, you do not have such upper bound and a lower bound. And for largest eigenvalue, you only have a lower bound. You do not have an upper bound, no matter you use column minor or row minor, okay? But a different thing for the smallest eigenvalue is if you use a column and row minor, you get an upper bound and lower bound, okay? And now, because what you remove is the column or rows of the bigger entry. So after you remove all the column or all the rows containing this big entry, there's no longer any big entry. Okay, so no matter you remove a row column or a row minor, a rows or the column. So actually this matrix is just the minor of the B matrix. And this matrix is just the minor of the B matrix as well. Okay, because there's no big entry. So this minus, they are the same. But this B matrix, they are very nice matrix because their entries are bounded by n to the minus epsilon. Okay, now, so if you can find some control on the smallest eigenvalue of these minors, then you will get a control on the smallest eigenvalue of the D matrix, okay? And this interlacing heuristic does not just apply to the smallest eigenvalue. It actually applies to many other eigenvalues as well. Okay, so it will also give you a control on the C transform if you can control the C transform of these two minors, okay, of this matrix B. So then, how to control the eigenvalue or the C transform of the matrix B? Now, actually, fortunately, we already have this result. Now, this kind of matrix, this B or BDC or BDR, they are called the matrix with bounded support. So the entry of them are typically of order 1/√, of n. But meanwhile, they also have the deterministic upper bound. Now, for this kind of matrix, in this paper of Huang and Li and Schnelli, they already show the eta star regularity at the edge. So you already have the control of the C transform, and also you have the control of the smallest eigenvalue. Okay. Now, here what I want to mention is this B matrix. So it's B matrix or the D matrix equal B plus C. Now, the variance of this Dij is 1 minus T, because my original variance of A plus Dij is 1, but the variance of A is of order T. Okay, so sorry, this is divided by n. Okay, so this is 1/n. But A part already take the variance T divided by n. So this D part actually only have a variance 1 minus T divided by n. Now this is also almost the variance of the B part, because the C part doesn't take too much variance. Okay, so if you want to find an estimate for the C transform of this B part or D part, you need to use the scaled Marchenko-Pass law, not the original Marchenko-Pass law. And also the estimate of the smallest eigenvalue of this B matrix will be the scaled left edge of Marchenko-Pass law, not the original left edge of Marchenko-Pass law. Okay. Now with this result for this matrix with bounded support, and also the interlacing, and then you can easily show that this SD has eta star regularity at the left edge. Okay, so this is a very basic minor argument to prove the eta star regularity. Okay, so now if you have the eta star regularity at the left edge of this D part, you can use the dynamic approach to prove that this lambda m of my Gaussian divisible model subtracted by the this random edge, and with the random scaling, you will have a Tracy-Widom law. Okay. Now, but notice that this lambda minus T is the left edge of the rectangular free convolution of my D matrix and the Marchenko-Pass law. But my D matrix is still random. Okay. So this guy is actually still random. And now this guy is also random, but here I just estimated it directly without showing the explicit formula because it's too complicated. So this randomness from this gamma n actually doesn't matter too much for the law of this smallest eigenvalue, but the randomness of this lambda minus T will matter very much. So because the randomness of this guy is from the D, and this D is actually a semi-heavy tailed matrix. So the fluctuation of this guy may be larger than the order n to the minus 2/3. So the remaining task is to find the fluctuation of this lambda minus T. Now, then you first need to identify this lambda minus T, but we know that this lambda minus T can be identified from this C transform equation with the subordination function, okay? And not trying to be too detailed, very roughly speaking, and eventually you can write this lambda minus T in terms of a function of this the so-called zeta minus T, which is a value you can estimate. So this value is the shift as left edge of the Marchenko-Pass law, but further subtracted by this term with of order T squared. So this is a very key shift. Now, and eventually, in order to study this lambda minus T, it will be equivalent to study this MD at this lambda minus T, more or less speaking, okay? So this MD is a C transform of the matrix D, and as I said, the spectrum of this D, the left edge of this D will converge to this quantity, okay? But now this parameter is away from the left edge of the limiting distribution of the spectrum of D by order T squared. Now this T squared is a mesoscopic quantity. Okay? It is smaller than order 1, but it's still away from this left edge. So this MD is a C transform, but with a parameter on mesoscopic scale, away from the support of the spectrum of this matrix D. Okay. Now, eventually, you need to study the behavior of this guy, the expectation of this guy, and the fluctuation of this guy. And after a further expansion, you can further replace this guy by its expectation, and especially for the fluctuation part, eventually it boils down to this quantity. So you need to study the fluctuation of this D transform of the D at the expectation of this zeta minus T. And around this, its expectation, okay? So now this guy is a linear eigenvalue statistic of this semi-heavy tail matrix. But it has a parameter on mesoscopic scale. So we call this quantity as a linear eigenvalue statistic on mesoscopic scale, or sometimes we just call it a mesoscopic statistic. Okay? And now how to study the fluctuation of this kind of linear eigenvalue statistic? Well, again, there is some literature on very similar problem. It's still on this semi-heavy tail case. And again, they study the linear eigenvalue statistic, say for this D, but it's a global parameter. So here, this Z is E plus I eta, and in their work, they study the case when eta is proportional to 1. So in this paper by Binoche, George, and Maltev, and also this work, which extend the results from Wigner to covariance, and they consider the linear eigenvalue statistic with this special test function, but with a parameter Z on global scale. So this Z is away from the spectrum by a global distance. Okay. Now, in this paper, they already derived the central limit theorem for this MD of Z by some martingale method. And actually, this method can be adapted to the mesoscopic scale. So even your Z is away from the spectrum by just a mesoscopic distance, this method is still applicable. So by following this strategy, we can finally prove that our mesoscopic statistic has asymptotic Gaussian law with this variance. So this method is more or less the same as the one used in their argument for the global statistic. So this is how you compute the fluctuation of the lambda minus t. So now when you have the fluctuation of the lambda minus t, and you also have the Tracy-Widom law for this difference, and then more or less you just get the final result, the phase transition for the Gaussian divisible model, but not the original model. Okay. Now for the original model, you need to do one more thing, namely they need to go back to the original matrix from the Gaussian divisible model. But due to time constraint, I'm not going to show you the detail. Eventually, it was done by something called the Gaussian green function comparison. So eventually, you want to compare this distribution with this distribution for the Gaussian divisible model. And it is well known that you can tend to study some functionals of the C transform instead. And one is for the Gaussian divisible model, and one is for the original model. So you're trying to compare compute the difference of these two guys. And this can be done by some expansion of these two functional with respect to the matrix entry, and then you use some moment condition or moment matching condition to get the cancellation between these two quantities. And this is basically a Lindeberg strategy. Okay, so you can replace entry either in discrete way or in continuous way, and then you use some moment matching condition to conclude the proof. Now, one difficulty in this comparison is, although our W matrix in this Gaussian divisible part is independent of the other randomness, our A matrix in this part, so remember this Y is A plus D, okay? Now this A is actually not independent of the D. So when you do the expansion with respect to this A entry, and you try to use the moment matching between A and W, actually you cannot treat A as some entry independent of the D and just use the moment matching to cancel out this entry, W entry, and A entry. So this is not so simple. You also need to consider the correlation between A and D, for instance. So this is a major complexity of the argument. But due to the time constraint, I'm not going to explain more detail. So I will just skip the last slides, and maybe I will just stop here. Okay. So thank you for your attention. Any question
Thank you
and
so much.
comment? Welcome. Yes.